So in this section, part 2, we're going to do experiments, weeks 5 to 8, and starting with the experiment where we used a redox reaction with permanganate to measure the percent composition of iron in a sample. And so we'll start out with some percent composition stuff. And here we have the determination of iron, so the experiment anyway. So very simplified percent composition, you have 26 red M&Ms in a bag of 200 M&Ms. You're assuming that all the M&Ms weigh the same, so without weighing an M&M and figuring out what the mass is, I think that's a reasonable assumption. And we can then take this type of equation, so we have 26 red over 200 total times 100%. Now, of course, these are individuals, but since they weigh the same, they're proportional to the mass, and that would be 13% red. Okay. So find the percent composition of copper in CuBr2. Well, this is a little bit more complicated because we have copper. Every atom of every different types has different mass, and of course, even some atoms of the same type have different mass. So that is isotopes, for example. So in this case, the copper bromide. We've got to figure out the mass of the copper, the mass of the bromide. And in general, what you do is you figure out the molar mass of the compound first. So you have copper is 63.55 grams per mole. And the bromine, so Br equals 2 times 79.90 grams per mole. And let's just figure out what that is quickly. It's actually 904 to be exact, so that is 159.81. And then we add equals that amount plus 63.55, enter, and we got 223.58. And now if we want to figure out the quantities, we just take equals 63.55, that's for copper, divided by the total mass over, or sorry, not over, backspace, times 100. And what do we have? We have 28.45% copper. So this is equal to 28.45%. Now if we look at the bromine, of course it's mostly bromine because bromine is a lot heavier and there are two of them. So that makes sense in terms of the copper. This here is the mass of the bromine, two bromine atoms, so we take the part over the whole again, equals this value divided by total mass times 100%, and we got 71.54%. And if we add this up, we should get 100. Let's see. Equals this plus this, and we get 100%, which figures. And it makes sense because bromine, of course, being heavier and being two of them, should be a lot more bromine there than copper. Okay, so let's go ahead and go to the next page. Now some more percentages. Here we have 23.99 for the Na. This is oxygen and this is hydrogen. So we have, and the total is 40.998. Again, the first thing you do is figure the molar mass of the compound in its whole, the whole compound. So that is Na, oxygen, and hydrogen. That doesn't look like an A. There we go. 23.99 over 40.998 times 100%, and this is grams and grams, so grams cancels. And for oxygen we have 16.00 over 40 grams again, 0.998 grams times 100. And here we have 1.008 over 40.998 grams, and this is grams again as well, times 100, and the 100 is percent. Notice that the grams in each case cancels, giving us percent as a unitless value, which it should be. Unless you're doing some odd percentages like mass volume or something like that, then your percent can have units. But the thing about mass percent is it really doesn't matter how you measure the mass. It could be grams, it could be kilograms, it could be pounds. As long as you're using the same units for everything, then your percentage will be the same. Okay, let's try this. So we have, I'm going to put the total mass here to make it easy. 40.998. And then we use, I'm going to go down one, equals 23.99. Divided by this value times 100. And that's sodium. I'll just write it down. Now let's do oxygen. Oxygen, we have equals 16 over, and I know it's 16.00, but with Excel it assumes infinite number of zeros. And that is oxygen, 39.02% oxygen. And now for hydrogen, equals 1.008 divided by this value times 100. The reason I separated this out a bit is now I can just do formula auto sum, and you can see that it adds up to 100, which checks out. Of course, hydrogen being the lightest has the smallest amount, oxygen, sodium being the heaviest, the largest amount, oxygen in between. It makes sense. Now, let's go and do another one. Here we have two of the same thing, so what we have to do really is figure out how much of each. I have nitrogen, hydrogen, and sulfur. Nitrogen is 2 times 14.007. Hydrogen is 4 times 1.008, and sulfur is 1 times 32.06, if I remember right, and yep, that is definitely what sulfur is, 32.06. And this is grams per mole, grams per mole, grams per mole. So 2 times 14.007 would be 28.014, and for hydrogen, 4 times 1.008 would be 4.032, and of course sulfur is just 32.06. When I add these together, my sig figs are going to stop at the hundredths place because that's the lowest, the least precise value. 4 plus 2 is 6, and I have 1 plus 3 plus 6 is 10, and 1, and this looks like 10 plus 4 is 14, and let's see, 2 plus 3 plus 1, 2 plus 3, this is 6, 64.106. And of course I stop here, so that's equal to 64.11. And now I simply take each of these values and divide it by the total. So I'll do it over here, nitrogen, hydrogen, and sulfur. Well, let's do it in Excel, then we can just run it faster. Just move this down a bit, and what I'm going to do is exactly the same thing. I'll put the total amount, and I'm going to go ahead and take it out all the figures, including the non-significant ones. I know I'm only good to 4 sig figs though. 64.106, and now we have let me go down here and I'll just say nitrogen, hydrogen, sulfur, NHS. So equals 28.04 divided by the total times 100. That gives you 43.74% nitrogen. And now we go 4.032 equals 4.032 divided by this times 100, and we've got 62.895. And now with sulfur, we've got equals 32.06 divided by this value times 100. And that's 50.0192. So basically 50.01, 6.289, not 210 actually, or 2890 because this would turn to this round up, and 60.290 and 43.74. Let's just add these up and double check. Auto sum, and that should enter as 100. Now it's very close to 100, so I'm happy it's 100 within 4 sig figs. So that would be how you do this one. Nitrogen is, what's it again? 43.74, 6.29, and 50.01. 43.74%, 6.290, 6.290%, and 50.01%. And when we added it up, of course, it added to 100, so we're good. Okay, let's go continue on. Here's solution stoichiometry. So here we're worried about the relative the stoichiometric ratios. So notice with this we're asking for silver chromate. How many grams of silver chromate, which means we have to figure out the molar mass of that stuff. And notice we have a ratio, 2 mol AgNO3 per 1 mol Ag2CrO4, or 1 mol Ag2CrO4 per 2 mol AgNO3. Okay, and those are the two things we're interested in. So first of all, let's figure out the molar mass of this guy. I have 2 times 107.87 2 times 107.87 grams per mole plus 51.996 rounds to 52.00 grams per mole. And then 4 times 16.00 grams per mole. And let's go ahead and I know this is 64, I know this is 52, and this I'll calculate out. 107.87, let's see. So let's go down one and say equals 2 times that's silver equals, this is basically, I'll go ahead and use 51.99, I think it's 998. I'll use a few more sig figs. 996. And let's go ahead and use all the sig figs we can. Why not? And now we just add it together. And we got 283.73. 283.73. Oh, wait. Wrong. This is equals 4 times that. How do we end it with? That's better. 331.73 is our number. Now all we need to do is say 0.150 liters times 0.500 mole per 1 liter times what is it? Over here we have 1 mole AgCrO4 over 2 mole AgNO3. Times 331.73. There we have it. And now all we need to do is go, okay, let's check our units. Liters cancels with liters. Moles AgNO3 cancels with moles AgNO3. Mole AgCrO4 cancels with mole AgCrO4. And we have grams Ag2CrO4. So, let's go ahead and crunch the numbers. Let's go ahead and do it here. Equals 0.15 times 0.5 divided by 2 times, and just use this value here, and that gives me 12.44001 grams. Of course, it's only good to 3 sig figs because that's how I know the volume and molarity of my solution, so it's 12.4 grams. So my answer is 12.4 grams Ag2CrO4. Final answer. Now here's a slightly different problem. We've got liters and liters, and basically we're trying to set up an equivalence and solve one side. I don't need to worry about molar mass because basically it's not asking for any mass. It's running an equation. The important thing is I have 3 mole of barium nitrate and only what I'm looking for is the aluminum sulfates, which is a 1 here. This is 1 mole aluminum sulfate. So I have 3 mole BaNO3, 2 per 1 mole 2SO4 parentheses 3. Or it would be the opposite, 1 mole BaSAl2SO4 3 per 3 mole BaNO3 2. Okay, so basically I'm setting this, the question is how many liters of this stuff. So I have X liters times zero point 0.280 mole barium nitrate per 1 liter times 1 mole Al2SO4 3 per 3 mole barium nitrate equals 0.025 liters times 0.350 mole Al2SO4 3 per 1 liter. So liters cancels with liters. Moles here, you have moles here. Moles here cancels with moles here. And liters with liters. So my units work out. What I end up with is moles of Al2SO4, Al2SO4 or aluminum sulfate on each side. Now we have to rearrange things a little bit. And what I want to do is divide out essentially what I'm going to divide by this ratio, which means no, not NO4, NO3 2, BaNO3 2, 3 moles, and per 1 mole Al2SO4 3. And then I have here 0.250, all this, so I've gotten rid of this, I've gotten rid of this, and now I want to divide by this, so I do 0.280 mole BaNO32 per 1 liter. And what do I have here? I have, again, this liter cancels with this liter, and I have moles of Al2SO3 cancels with moles of Al2SO3. Moles of Ba2NO3 cancels with moles of BaNO3 too, I mean. So barium nitrate cancels. Aluminum sulfate and aluminum sulfate cancels. And what I end up with, the only thing that doesn't cancel is 1 over liters. Of course, that liters flips up on top, and that gives me units of liters, which is what I want, since I want liters. So let's go ahead and just dump all of this into Excel and see what we get. Crunch the numbers. So we have equals 0.025 times 0.350 times 3 over 0.280, and that's about it because the other one is just 1, which is the same as not dividing by anything at all. So what we have, that's 0.90937 or 93.7 ml, sort of ran out of room here. 93.8 because the 5 rounds up, so it's 93.8 ml or 0.0938 liters. And it looks like we're good to 3 sig figs all around, so that's where we are. That's our answer. Okay, let's keep going. So here's something that's a little more like what we were doing in the acid experiment. So here we have um, 496 moles per liter of HCl and 2.0 and 0.02 liters or 20 milliliters of 0.809 moles per liter NaOH. So we can set up the same type of problem. It's a little bit easier because it's a 1-to-1-to-1 ratio, but we'll just put that in for good practice. So we have X liters times 0.496 mole HCl per 1 liter. It's a solution essentially. Times 1 mole over 1 mole HCl equals 0.0200 liters of times 0.809 mole NaOH per 1 liter. Okay. So if we want to rearrange things, we divide by 0.496 and everything else is 1, but I'll go ahead and put it in. X liters equals 0.0200 liter times 0.809 mole per liter NaOH times 1 mole HCl per 1 mole OH. And then you divide that times 0.496 mole per liter HCl. So moles NaOH cancels with mole as NaOH, mole HCl cancels with mole HCl, liters cancels with liters, and again I have 1 over 1 over liters, which is equal to liters. That's my units. And crunch the numbers. Can I move it here? So we have here equals 0.02 times 0.8 09 divided by 0.496, and we've got 0.0326 or 32.6 ml or so. Or 0.0326 liters. Final answer. How many liters of 0.15 molar HCl are required to neutralize 1.25 grams of sodium carbonate producing carbonic acid? Well, obviously, you know, this reaction doesn't end up here. It turns into carbon dioxide and water, but that doesn't matter too much. What we're really interested in is the ratio of this to this. So the first thing I notice is I have 1 Na2CO3, 1 sodium carbonate per 2 HCl. And we need to find out the molar mass of sodium carbonate, so we have it's 2 times 23.99 and 1 times 12.011 and 3 times 16.00. Let's just use the more precise mass of. We can always round it. And it looks like I have all these. I have a space here, so I can just insert AutoSum, done. And we've got 107.99. Yeah, 107.99. And it looks like that's about as far as we can go. Yeah, 107.99. So this is 107.99 grams per mole. Good. And now we take .715 let's see, so grams with grams here, moles flips up on top, so we're good there. Now what I want to do is take and divide each side, so I say times two mole HCl per 1 mole sodium carbonate, and then I have divided by 0.715 mole per liter HCl. So let's see what we have. We have mole HCl cancels with moles of HCl. Mole Na2CO3 cancels with mole Na2CO3, and grams Na2CO3 cancel with grams Na2CO3. So what we're left with is 1 over liters HCl, which is equal to liters of HCl. And we've crossed that out and crossed this out as well. So we have X liters equals grams per mole. And again, let's just cancel these out again. We have grams Na2CO3 and grams Na2CO3, moles with moles, moles HCl with moles HCl, and essentially I'm ended up with the 1 over liters again, which is liters. And let's just calculate that out. Equals 1.25 times 2 over open parentheses 107.99 times 0.715. Shift close parentheses. And what do we get? 0.032 liters to 0.0324 liters, or I should say, equals 32.4 ml. Oh, 324 liters. There we go. So here we have more stoichiometry problems. 1 mole NaOH. What is the molarity of NaOH if it takes 4.40 exactly 40 milliliters of NaOH to reach equivalence point in titration of with 50 milliliters of 2 molar HCl. So basically we have NaOH plus HCl makes NaCl plus H2O. And so it's a 1:1:1 ratio. So I have So I'm sort of skipping one piece here, and I'm taking account it's a 1:1:1 ratio. So I'm not including the stoichiometric ratio because it's 1. So we simply say x equals 0.050 liters times 0.20 mole per liter over 0.040 liters. So liters cancels with liters, giving me units of moles per liter. that is 0.25 molar. Good. So we have 50 milliliters of 3.00 molar potassium hydroxide are required to titrate 60 milliliters of H2SO4. What is the molarity of the H2SO4? Exactly the same thing. You have X mole, or not exactly the same thing. Let's write the equation before we do anything else. Well, why don't we change color just for the fun of it? Let's see. So we have so notice we have one potassium here, we have two potassiums there, so we need two of these, and I have 4 hydrogens and 2 oxygens. I need 2 waters to make 4 hydrogens and 2 oxygens. And now we're good, but notice I have a ratio of 2 mole KOH per 1 mole K2SO4. And now we can set up our equation knowing that. So I have X mole per liter H2SO4 times 0.600 liters. 6 point, sorry. Times 0.0600 liters times 2 mole zero point 0.05 liters times 0.0300 mole per liter KOH. And I have some space up. Well, first of all, let's go ahead and do the division. So what I'm going to have to do is divide by 2, multiply by 1, and divide by 0.06 to give. So that gets rid of this, gets rid of this and this. So let me move this up here. So I have X mole H2SO4 per 1 liter H2SO4 equals close that out. Zero 0.05, 0.3. Now I actually have to divide by 2. It's always good to keep your units. Oh, come on. So we have divided by 1 mole H2SO4, and now we have 0.600 0.0600 liters of the solution. So we have you have moles of KOH cancels with moles of KOH, liters cancels with liters, and now I have moles of H2SO4 per liter, which is the units that I want. And let's go ahead and plug that in. Equals 0.05 times 0.3 divided by shift open parentheses 2 times 0.06 shift close parentheses okay, well, it looks like I hit the wrong key here. Backspace 2 times 0.06. That's better. See if it likes that. And it looks like I have 0.125 mole per liter, which is reasonable, considering it takes twice as, more of the H2SO4. Well, it's more milliliters, yet that's requires twice as much KOH. So it's logical that it would be a smaller concentration. So this is 0.125 mole per liter. Okay, let's keep going. Fruit Loops. Calculate the molarity in moles per liter. It's 57 grams per 300 milliliters of water. So that would be, you have to figure out the molar mass of sodium chlorate. This is the same thing, you're just figuring molarities. And this is M1V1 equals M2V2. So these are fairly straightforward. Okay, calculate the molarity in moles per liter. 57 grams of sodium chlorate in 300 milliliters of water. So we have, we have sodium is 23.99, chlorine is 35.45, and 3 times 16 would be 48. it looks like it's 107.44 grams per mole for the uh, molar mass of sodium chloride. So we take 57 grams times divided by 107.44 grams per mole times 1 over 0.300 liters. And it looks like I'm limited to 2 sig figs by the 57. Let's see. .1591, so 0.16. So this is equal to 0.16 mole per liter. Notice that grams cancels with grams, moles flips up on top, and then we have 0.16 mole per liter. 2 sig figs, we're good. Same idea here, we just have a different compound. And in interest of time, you can solve that one. Same thing, you figure out the molar mass, you divide by the liters of water. First you divide the grams by the molar mass, then divide that by the liters of water. Let's try this one because it's different. So we have how many grams of, oh wow, in 1 point it needed to make a oh no, actually this is not M1V1, it's not. So we have NaOH. It's a little bit different though, in that we have we're asking for grams. So we have, let's just solve it. X grams divided by, well, we have 23.99 plus 16.00 plus 1.008, and if I remember right, this is 49.998 grams per mole. 49.998 grams per mole equals times 1 over 0.10 liters equals 3.0 mole per liter. So again, we would multiply and divide to put the x on one side. So we have x grams equals 3.0 mole per liter times 0. 0.01 liter times 49.998 grams per mole. And what we have is moles cancels with moles, liters with liters, and you end up with grams. So we have x grams. So let's just write this out. X equals 3 times 0.1 times 49.998, and it looks like I'm good to about 2 sig figs. So this would be 0.3 times 49.998. Let's see what that is. Equals 0.3 times 49.998. And we have, oh, I must have messed up, equals 0.3 times 49.998. That's better, 14.994 grams. $15 grams to round it up. And here are a couple more problems, and then let's call it a day. If I add 25 milliliters of water to 135 milliliters of 1 molar NaOH solution, what will the molarity be? Here we have M1 V1 equals M2 V2, the solution. So M1 is, we're solving for M2. M1 is 0.150 times, let's just solve it first, and then let's solve the M1 V1 thing first, and then it's easier to do that way. Let's get rid of this. So what we want is M2, so what we're going to do is and so M1 equals 0.150 mole per molar. V1 equals 135 ml, and V2 equals 25 ml plus 135 ml. So 135, 25, 5 plus 5 is 10, 3 plus 3 is 6, and we have 160 ml. So V2 is 160. So let's go ahead and put stuff in. We have M2 equals 0.15 times 135 over 160, and this is molar, this is ml and ml. You don't have to convert to liters when you do this because ml cancels and you end up with molarity. You can use any volume as long as you're consistent with the volume. In fact, you can use any concentration as long as you're consistent with the concentration. Any concentration units, that is. So what is M2? We've got 0.15 times 135 over 160 equals 0.15 times 135 over 160. And you have 0.126, which is slight dilution. It makes sense. You've got a smaller amount. 0.12656, so 127 actually. 0.127 ml. And it looks like it is a 3 sig fig thing, so 0.127. Sorry, not ml. Mole per liter. 0.127 mole per liter. So here we have the same thing. I have M1 V1 equals M2 V2. And what I'm solving for now is V2. So we have V2 equals M1 V1 over M2, which is equal to 2.00 times 100 over ml. This is molarity. And M2 is 0.150 molarity again. So molarity cancels this molarity, giving me milliliters. So 0.2 times 100, 2 times 100 over 0.5. Let me just write that down, equals 2 times 100 all over 0.15. Okay. And that is a big number. It's 1.3 liters, 1.33 liters. Is what my total volume will be. And that's up to basically week 8, so stay tuned for the next installment.